Now let's use Vsepr to find some molecular shapes. So we'll call this lecture Vsepr Ii. So suppose our molecule is CO2. The first thing we need to do is count the electrons. So carbon, being in group 14, has 4 electrons. Oxygen, being in group 16, has 6 electrons. There are 2 of them, so we have 12 electrons from oxygen. When we add 4 and 12, we get 16 electrons total. Next, we draw our skeleton. So we put the carbon in the center, since it's least electronegative, and the 2 oxygens peripheral to give us the highest possible symmetry. The third thing we were going to do is count the remaining electrons, subtracting 2 for each bond. So we have 1 bond there and 1 bond there. We had 16 electrons to begin with, minus 4 since we have 2 bonds, and that gives us 12 electrons remaining. So we fill in our remaining 12 electrons such that everyone's octet is satisfied, and it turns out that each oxygen gets a double bond. Right, so that oxygen has 2, 4, 6, 8 electrons. And the other oxygen is in exactly the same boat. The carbon has 2, 4, 6, 8 electrons. So the carbon is happy. This means we now have the correct Lewis structure. So now we need to count the number of electron domains on the central atom. So we have 1 electron domain, 2 electron domains. So here's a picture of our 2 electron domains. Our central atom, the carbon, will be right there. And then we'll have an oxygen here and an oxygen here. And as you can see, we get a linear molecule. Now let's look at a different case. How about the nitrate anion? Counting the electrons, we get 5 from nitrogen, 6 from each oxygen, so 18, and we add 1 to account for the -1 charge. And that gives us 24 electrons. Now we draw our skeleton with nitrogen in the center. And at this point, we count the electrons we've used. We have 3 bonds. Each bond represents 2 electrons, so we've used 6. That means we have 18 left to fill in. And in order to do that in such a way that satisfies all octets, one of the oxygens has to be double bonded, like so, and the other 2 can be single bonded. Now that oxygen has 8 electrons, as does that one. That oxygen has 2, 4, 6, 8 electrons. And the nitrogen, 2, 4, 6, 8 electrons. So we can be content that this is the correct Lewis structure. And it turns out we could make 2 resonance structures simply by moving the double bond. So for instance, we could put the double bond on the central oxygen, or we could put the double bond on the oxygen on the right. So those are the 3 equivalent resonance structures for the nitrate anion. Oh, and since it's an ion, we have to put brackets around it and indicate the negative charge in the upper right-hand corner. So now we can go ahead and count electron domains. Here's our Lewis structure once again. And on the central atom, which is the nitrogen, we have 1, 2, 3 electron domains. So when you have 3 electron domains, your electron domain geometry is trigonal planar. Our central atom will be here. That's the nitrogen. And then there's an oxygen going away from you. There's one coming towards you. And there is the other one going away from you. So our electron cloud geometry is trigonal planar. And our molecule is trigonal planar. Now let's look at something more complicated. How about sulfur hexafluoride? First thing we'll do is count electrons. The sulfur is in group 16, so it has 6 electrons. Fluorine being in group 17 contributes 7 per atom. Since there are 6 fluorine atoms, we get a total of 7 times 6, or 42 electrons from fluorine. When we add 6 and 42, we get 48 electrons total for the molecule. Now we draw our skeleton with sulfur at the center, and we arrange our 6 fluorines around it, thusly. And now we can count remaining electrons. We've made 6 bonds, 1, 2, 3, 4, 5, 6. That means we've used up 12 electrons and we have 36 more to go. Well, it turns out that for each fluorine to have its octet completed, each fluorine needs 6 more electrons. So if we put 3 lone pairs on each fluorine, we are good. So now that is our complete Lewis structure. And to count the electrons, you can just realize that there are 8 electrons around each fluorine, and there are 6 fluorines. 6 times 8 is 48. So we know this is our correct Lewis structure. Now we need to count electron domains around the central atom. There's one, there's one, there's one, there's one, there's one, and there's one. That means we have 6 electron domains. And if you recall from the previous lecture on Vsepr theory, when you have 6 electron domains, you get sp3d2 hybridization. There's a picture of it. Our central atom, the sulfur, will be right here. Then we have 2 fluorines coming out towards us. There they are. And then 2 going back away from us, like so. And then 1 up above, and 1 down below. And this is an octahedral electron domain geometry and an octahedral molecule. Now why don't you try some on your own? How about sulfur dioxide and ammonia and xenon tetrafluoride? In each case, you'll find that all have lone pairs on the central atom. That means that the molecular shape is a derivative of the electron cloud geometry. That is, the molecular shape is related to the electron cloud geometry, but not the same as the electron cloud geometry. So work those on your own. Thanks for watching.